The total amount of money that we have doesn't change. It's just a transfer. So this is very similar to what energy is. What is up, guys? Welcome back to another lecture series. Today we'll be covering chapter 6 on energy. Before we go into energy, I want to draw a very similar concept, which is money. Let's think about what money is and think about how we are going to be using money. So money is something that we all have. Some of us have a lot of it, some of us have very little of it. But the thing about money is it cannot be destroyed. You can't destroy money unless you physically burn the currency, but that is not legal. Okay, so we just take it as money cannot be destroyed. Money can only be transferred from one person to another person. If you go down to the hawker center to buy chicken rice, you're gonna pass your money to another person. We say that it's a payment, but actually what we are doing is that we are giving our money to someone else. So there's a transfer of money there. But the total money between the two of us remain the same. For example, if I'm giving $5 to the chicken store owner, the chicken store owner receives my $5, but amongst us, that $5 is still there. The total amount of money that we have doesn't change. It's just a transfer. So this is very similar to what energy is. Energy cannot be destroyed, and energy is only transferred from one store to another store. What is this concept of energy store? There's going to be a few energy stores that we'll be discussing, but in general, an energy store is where you store energy, just like your banks. Your bank account is where you store your money, and energy store is where you store your energy. So I can move the money across banks. I can also move energy across different energy stores. What are these energy stores? Number one, we have kinetic store. So kinetic store is an energy store that is possessed by moving objects. If an object is moving, we say that this object has a kinetic store. Say for example, my calculator. If I'm moving my calculator up and down, then I'm transferring energy from whatever store that I'm holding to the kinetic store of the calculator. Number two is the gravitational potential store. Every object in a gravitational field, like the one of Earth, will possess energy in its gravitational potential store. It's just that when we lift the object higher, then the gravitational potential store of the object will increase because I'm going to be storing more energy as I lift it up. When I drop it, it's going to release the energy. So the higher you go, the more energy you can release when it's dropping. So that form of energy release could be in the form of heat. It could be the kinetic energy of the object. Number three, we have chemical potential store. Chemical potential store, these are energy stored in chemical bonds. For example, your fuel, your food, fossil fuels, food, and your batteries. We say that there's energy in the chemical potential store of these items. And this energy is released through chemical reactions. Okay, when chemical bonds are formed, they will release this energy. Number four, we have the elastic potential energy, or energy in the elastic potential store. The energy in the elastic potential store can be increased when we stretch an elastic object. When we stretch any object, we will increase the elastic potential store of that object. So it's most commonly found in rubber bands or any elastic objects, like a stretchable rope. Number five is the nuclear store. Nuclear store is energy stored in the atomic nuclei. So we know that atoms have a nucleus, and within the nucleus, there's actually energy that is stored in this nucleus that can be released through nuclear reactions. Just remember that nuclear store is the energy that's stored in the atomic nuclei. Number six is the internal store. So internal store is the energy that's stored in particles. Specifically, we are looking at the micro level. We are looking at the individual particles. And what kind of energy do they possess? They possess the kinetic energy, and the potential energy. When you have particles of matter, these particles are constantly moving. If they are constantly moving, it means that they'll possess some form of kinetic energy. So that is part of your energy in the internal store. Also, there are going to be attractive forces, because the particles will experience your intermolecular forces of attraction, and if they are separated by a certain distance, there's going to be potential energy. Okay, potential energy arises when you move objects against the force. For example, on the surface of Earth, I have a ball, and this ball experiences a weight. When I move this ball to a higher level, there is going to be an increase in the energy stored in its gravitational potential store. So the potential energy increases for this ball. So same thing with particles, the analogy is the same. When you move the particles further apart, then the potential energy of the particles will increase. Okay, this kinetic energy is going to be different from this kinetic energy, because for this one, it's on a macro level. We are looking at the actual movement of the object. For this kinetic energy within the internal store, we are looking at the microscopic level. We are looking at the movement of individual particles. So an object can have zero kinetic store, but still have internal store. Next concept is on the pathways to transfer energy. So there are going to be 4 or 5 pathways to transfer energy depending on how you classify it. In general, I will use this acronym MEHPP. M stands for mechanically. You have a box, you apply a force, and it causes the box to move by a distance s. This is a mechanical form of energy transfer, because a force applied over a distance is work done, and that is a mechanical form of energy transfer. If we want to put it in words, it will be as such. Let's say this is pushed by a man. The energy in the chemical potential store of the man is transferred mechanically to the kinetic store of the box. This is how we phrase it. We look at the initial store, we look at the transfer method, and then we look at the final store. Okay, you can think of your transfer method as payment methods. Like we said, energy is like money. Energy stores is like your bank accounts. This one is like the way you transfer money. Like your PayNow, you got your PayLah. For those who are not from Singapore, your bank transfers, your check, these are all possible payment methods. And that is very similar to what we have over here for the transfer methods of energy. Next is electrically. So electrically, let's say you have a battery which is connected to a heater. The energy that is stored in the battery is chemical potential. The energy will be transferred from this chemical potential store of the battery to the heater. Okay, the heater will release heat, so that is actually the internal store of the heater. Put it in words, energy in the chemical potential store of the battery is transferred electrically to the internal store of the heater. Next, H is for heating. Look at a scenario of a fire. Okay, let's say the fire is burned by some wood and it actually heats up the water. Okay, why would there be transfer of energy through heating? Because the fire is at higher temperature than the water. We say that the chemical potential store of the wood is transferred by heating to the internal store of the, let's call this the pot, okay? And the internal store of the water is transferred by heating to the internal store of the pot and the internal store of the water, and that causes the temperature of the water to increase. Lastly is P. P stands for propagation of waves, but there are 2 kinds of waves that we can discuss. Propagation of waves. The first kind of waves is what we call mechanical waves. Mechanical waves are physical waves like your sound waves, your water waves, waves that you can see. For example, I'm just putting a speaker connected to a battery. So the energy in the chemical potential store of the battery is transferred electrically to the kinetic store of the speaker. because the speaker is going to vibrate. So it moves. When the speaker moves, there will be energy in its kinetic store. Then, energy in the kinetic store of the speaker is transferred by propagation of sound waves. You can say mechanical waves, but since we already know that it is a sound wave, we will just say sound waves. 2, you have a boy standing over here, and this is ears. He hears the sound coming from the speaker. Okay, and when he hears the sound, it's because his eardrums are vibrating. We will say it's transferred by propagation of sound waves to the kinetic store of the eardrums. The other type of waves is going to be electromagnetic waves. Electromagnetic waves are waves that we cannot see. We will cover this more in detail in the chapter of electromagnetic waves. But for now, you can think of waves as being your light. Let's say we have a situation where we have the sun, and the sun is shining down on a boy who is standing on the ground on a very hot day. We can say energy in the nuclear store of the sun, because the energy from the sun comes from nuclear reactions. So energy in the nuclear store of the sun is transferred by propagation of electromagnetic waves to the internal store of the boy. The boy's body temperature heats up, so it transfers to the boy. So these are the energy transfer methods. The next thing we will talk about is the principle of conservation of energy. There are 3 points that you need to know for principle of conservation of energy. Number 1, we need to say energy cannot be created or destroyed. Full stop. Number 2, it can only be transferred from one store to another. And number 3, the total energy of an isolated system remains constant. What is this isolated system? An isolated system is one where there's no energy entering or exiting the system. We can use this for a variety of questions. Let's say you have a ramp with a ball dropping down. This ball is at a height of 10 meters. And assume there's no friction along the ramp. Find out what is the speed of the ball at the bottom of the ramp. Before we go into the question, we need to know a few formulas. Number 1, gravitational potential energy has the formula of mgh. M is the mass of the object, G is the gravitational field strength, and H is the height. On the ground, we will consider the GPE to be 0. And as you ascend to a higher height, the GPE will increase. How much does it increase by? It depends on the mass of the object as well as the increase in height. Ke is given by half mv squared. If I want to find the kinetic energy possessed by a particle or any object, I'm just going to take half multiplied by the mass of the object multiplied by its velocity squared, which will give me the kinetic energy. Energy has the units of joules and is represented by the symbol J. So now let's look at this question. When the ball rolls down the ramp, it's going to lose GPE because its height decreases. It decreases by 10 meters. So it's going to lose 10 meters equivalent of GPE. This GPE will go towards the KE because there's no other places for the energy to be stored in. We can write that the loss in GPE is equal to the gain in the kinetic energy. The loss in GPE is going to be mgh, whereas the gain in Ke is given by half mv squared. You notice that both m's can be cancelled on both sides of the equation, leaving us with gh equals to half v squared. G is the gravitational field strength of Earth, which is 10. H is 10 meters, half, and v is what we are trying to find. So we get v squared to be equal to 200, and v will be equal to 14.1 meters per second. Next concept is on work done. Work done by a constant force is defined as the product of the force and the displacement moved in the direction of the force. Mathematically, WD is equals to Fs. F is the force, S is the displacement in the direction of the force, and WD is work done. What is work done? Work done is nothing more than a mechanical transfer of energy. Say for example, you have ground here, you have a box on the ground, and we are applying a force of 20 newtons on this box. It causes this box to move by a distance of 5 meters. You apply a force of 20 newtons to the right, and the box moves towards the right by 5 meters. So we are doing positive work on the object. Okay, so the work done by the force of 20 newtons is going to be positive. Specifically, we can use the formula to find out how much energy we input, how much work did we actually do. We take 20 times 5, we get 100 joules. This 100 joules of energy is supplied to the box. You can think of it as an energy supply, because when you push the box, you are actually introducing energy to the box. Two variations. Number one, what if the box didn't move? You push very hard on the box, but the box just stays put. Then what is the work done? Well, if the box didn't move, that means your displacement is 0. And since work done is force times displacement, your work done must also be 0. What are the implications? It just means that if you push something and that thing doesn't move, like when I push a wall, it doesn't move, then the work done on the wall will be 0. So it's not about how much effort you put in. It's about the actual movement of the object and the force applied. Number two, what if now there's friction on the ground? What happens? Is the work done the same or is it different? Let's say there's friction on the ground. That means that over here, there will be an opposing force to the left side when we are pushing the box to the right. Let's say that force is 5 newtons. A constant frictional force of 5 newtons. We can find the work done against the 5 newtons. You see, because the force is going to the left and the displacement is going to the right, we know that the work done by the 5 newtons friction must be negative. If the work done by the 5 newtons is negative, I can simply write work done against the 5 newtons. Okay, and that will give me a positive value. The negative work done by the 5 newtons is equivalent to the work done against the 5 newtons. Let's calculate the value. We are just going to take 5 times 5. 5 newtons times 5 meters, giving us 25 joules. What is the implication of this? When we do work against an object, it means we are removing energy from the object. When we do work on the object, we are introducing energy to the object. So while this 20 newtons is introducing energy, this 5 newtons is removing energy. The net energy gained by this object would be the difference between this work done, 100 joules, and the 25 joules. So my net work done on the object is going to be 100 minus 25, giving me 75 joules. If there are no other external forces, then this 75 joules will go towards the kinetic energy gained, which means this box will gain 75 joules of kinetic energy. Without the friction, it will gain 100. With the friction, it will lose 25. Therefore, it only gains 75. That is work done concept. As long as there's a movement in the direction of the force, that's work done. Another question, if let's say they tell you that we are pushing the box up a slope instead. Now this time, how do we calculate the work done? Let's say I'm pushing it up by 5 meters and the box actually moved up by 5 meters. I also know that this distance is 4 meters and the height of the slope is 3 meters. This is where it gets a bit tricky. So you need to be very sure of the concept that we are using. Work done means force times displacement in the direction of the force. Say this object has a weight of 10 newtons. It's being applied a force of 30 newtons. So there's a 30 newtons force pushing it up and the weight is 10 newtons. How do we find what is the work done? How do we find what is the energy of the box at the very top? Let's go through. So the work done by the 30 newtons force will always be the 30 newtons times the displacement moved in the direction of the force. When the box moves from here to here, its displacement is this upwards sloping arrow. Okay, this diagonal arrow pointing to the top right hand corner is our displacement, which means that the displacement is going to be 5 meters. 30 times 5, that gives me 150 joules. We are introducing 150 joules of energy to the box. At the same time, you can see that there is a 10 newtons force downwards, which is the weight, and the object is being moved upwards by 3 meters against the direction of this 10 newtons force. We can say that the work done against the 10 newtons is 10 times 3, giving us 30 joules. The work done against the 10 newtons force is also the same as the gain in GPE of the object. If you don't believe me, let's test this out. GPE is mgh. Well, my mg is 10, my h is 3 meters, because the height increases by 3 meters, which means my gain in GPE is 30 joules. 30 joules is the same as work done against 10 newtons, which also means that the work done against the 10 newtons is the gain in the GPE. So think of the box as a system, right? I'm supplying 150 joules of energy, but 30 joules of this energy is going towards the GPE, or is being lost from the system. The object will possess 120 joules of energy. This 120 joules of energy is your kinetic energy, because there's no other stores for the energy to be in. It must be in the kinetic store. Unless there's friction, then it will be reduced, but otherwise it will be the kinetic store. Next concept is on power. So power is defined as the rate of energy transfer. It's given by the formula P is equals to E over T. Say for example, you and your friend are going to raise up a tall building. You want to see who is faster at climbing this tall building. This tall building is 30 meters. You and your friend both weigh the same 50 kg, and the gravitational field strength is 10 newtons per kg. You took a time of 10 seconds, very fast. Your friend took a time of 20 seconds, slightly slower. Okay? Let's calculate two things. Number one, what is the energy output of you and your friend? Number two, let's calculate the power. Right, so for energy output, we know that the energy that you and your friend are gaining when you are climbing the stairs is the gravitational potential energy, which is given by mgh. M is the mass, 50, G is 10, and the height is 30, which means the GPE is 15,000 joules. You and your friend, in the process of climbing to the very top of the building, would have gained 15,000 joules of energy. But the rate at which the energy is being transferred to you and your friend will be different, because the time taken for you to reach the top is different from your friend's time to reach the top. Let's calculate the power for both you and your friend. So power of you is the energy, which is 15,000, divided by the time taken for you to climb up the entire flight of stairs, which is 1,500 watts. The units for power is watts, W-A-T-T. Your friend's power is going to be calculated the same way. 15,000, the total energy, divided by the total time taken, which will give us 750 watts. So even though the energy gained by both you and your friend is the same, you guys probably consume the same amount of calories to reach the top, but the power output by you is a lot higher than the power output by your friend, which is why you may feel a bit more tired, because you need to respire at a faster rate to support the higher power output. Next, let's cover the concept of efficiency. Efficiency is a concept used only if there is power loss. So efficiency is defined as the ratio of the useful energy output over the total energy input. Let's go back to the example of climbing up the stairs. Your energy output is 15,000. That is your useful energy output. However, your body may consume more than 15,000 joules of energy in order for you to produce 15,000 joules of energy. So let's say your useful energy output is 15,000, but the food that you eat is 30,000, which means that the efficiency of this process is only 50%. For every joule of energy that you consume, you will only be able to use 50% of it for your intended purpose, which is to climb the stairs. This concept is more used in actual appliances or actual things that involves energy. For example, your car. We always talk about the efficiency of the engine. If I am putting in 1 joule of fuel into the petrol tank, then the energy output of the car is 0.2 joules. Then my efficiency is 20%. Okay, so the useful part matters. For a car, the useful energy output is the kinetic energy moving forward. That's useful. What's not useful is the heat generated. That's not useful energy because it doesn't serve the purpose of the car's movement. So we say that this 0.2 joules is useful. The 0.8 joules, which is lost to the surrounding as heat, is considered non-useful energy. So my efficiency is only 20%. There are different sources of energy. You have renewable and non-renewable sources of energy with different efficiencies. Number one is fossil fuel. Fossil fuels are fuel that are obtained from deep underground. Okay, it's cheap. It's the most reliable. Okay, however, the efficiency is very bad actually. It's like 40%, 45%, thereabouts. This is non-renewable. Your nuclear fuel is also non-renewable, and the efficiency is about the same as your fossil fuels, less than 40%. Your biofuel is from plants, and this is considered to be renewable because we can always grow more plants, but we can never get back the fossil fuel that we consume. Same thing for nuclear. If we are using a finite resource, that will be considered a non-renewable source of energy. If the resource is not finite, then we will consider it a renewable source of energy. So like a biofuel, like your wind energy, like your hydro dam, hydropower, okay, geothermal energy, all these are possible energy sources. Alright, and all these are renewable. That's all from me. I hope this video has helped you. All the best.